Yes, I'm not very far, but this is the hardest, in some sense, the hardest part and the most important things to say. Okay, so yeah, I do want to actually prove you a theorem. So remember there were some axioms which were not axioms, and in this chapter there's also a theorem which is not a theorem, which is the Clifford-Hammersley theorem, which is only a theorem under an appropriate assumption, extra supplementary assumption. So I want to certainly prove that theorem because it actually has a proof of a couple of formulas, which Solomon does give in a restricted. He gives what is really the correct proof of the Clifford-Hammersley theorem in the discrete case, the finite case. And he says it's also correct in if you have continuous densities, and I don't understand why he wants to. Anyway, I would say differently. Let me think. Now, first, next. Okay, so well, first of all, I can just remark we saw some axioms of some properties of conditional independence. And what we saw, and one of those properties was a property which we can only be sure of if the joint probability density is positive. But so we may be prepared to make that assumption. And they mean if you just use those axioms, the first four or all five, you can deduce many conditional independencies from a few of them. And both for this situation and for this situation, in particular, so let's do it over here first. There's something called. So these are some kind of elementary things which are important to know if you want to do anything with these graphical models. In the case of the underactive graph models, so I have now erased what the model is, but I did tell you. Yeah, there is something called, I get them in the right order, there is something called a pairwise Markov property. They're called Markov properties. There's something called a local Markov property, and there's something called a global Markov property. Now the global Markov property is the defining property, the one I told you. So XA is independent of XB given XS if S separates A from B. And if this is true for all A, B, and S, such that S separates A from B, then we say the joint probability distribution satisfies the global Markov property. And we can immediately deduce lots more conditional independencies by using those basic rules. And it's trivial to see that one of them is what is called the local Markov property, which is that XV is independent of almost everything else. V, the whole set, minus V itself, and minus the neighbors of V. So how should I write this? Union neighbors of V. Given X, NB stands for neighbors of V, so of little v. So that means that it's a bit like the Markov, the more complicated, so-called Markov blanket I told you about over here, which was the fathers and the children and the siblings. But here, the neighbors. Conditional on the neighbors, this variable is independent of all the other variables in the graph. And that follows trivially from here. And what is not so trivial is the fact that you can go, they're actually equivalent if you have those, you can just use those 5 rules to go from here to here. So we don't need to assume positivity or whatever, but we do have to assume sort of the 5th axiom.
I mean, you go from local to global.
Yes, so you can go the set of all local
ones,
conditional independences. Let me say something which I know is true. The set of all local Markov properties implies the set of all global Markov properties if the joint probability distribution satisfies those 5 rules. So in particular, in the case when all probabilities densities are positive, so that means there are no zeros in the joint probability of each of all variables. So there are no combined outcomes which are impossible. So it's annoying because that means there's some sort of strong deterministic. There's some deterministic relation here because this is impossible. You're never ever going to see somebody with these properties and these properties and these properties. And this is supposed to be all about dependence and independence, and it can't handle, the theory can't handle deterministic relations. It gives the wrong answer or it doesn't get stuck. Okay, and there's also a pairwise, and that is, suppose V is not an H of V prime. Sorry, there's no H from between V and V prime. Then XV should be independent of XV prime, given everything else. So then, of course, they're different. This is called. It's a bit odd that this should be weaker than this, but it is. You can easily see that this implies this by using the axioms, because one of the axioms was if you've got a whole bunch of random variables here, you can add some of them to the conditioning set, and then what's left is still conditionally independent of what we had. So in here, in V minus, in the set of all variables minus V and V prime, there are all names of V. And here's XV and here's XV. And XV prime is the only one, is the one which is left. So this local implies pairwise by using the rule that you can move some variables to the conditioning side.
So that doesn't mean the 5th annoying.
That's not the 5th annoying one. No, no. So, okay, now the first four are called the semi-graphoid axioms, and the 5th is called the graphoid. All 5 together are called the graphoid assumptions and axioms. And the reason they're called that is because the separation in undirected graphs satisfies all 5 axioms. If you say XA is independent from XB given XS, if S separates A from B, you just, instead of talking about conditional independence, you just talk about graph separation. Then there's all 5 axioms are true. And that's why they're called graphoid axioms. And the first 4 are called semi-graphoid axioms because they're not all 5. But actually all 5 are not enough to characterize graph separation. So there's just things where it's computer scientists and logicians and some pure mathematicians do a lot of work on. Okay, so just using those 5 axioms anyway, you can, sometimes when you're using the first 4 of them, you can show that this implies this, implies this. And therefore, for all positive probability densities, this random variables having a joint, for all joint distributions which have a positive probability density with respect to a product measure, blah, blah, blah. For instance, in a discrete finite case, when all the basic, sort of most finely specified probabilities are positive, so every combined value of all variables are possible, then the pairwise implies low. They're equivalent, sorry, they're equivalent. Okay, now I think I'm not going to do it now, but for directed acyclic graphs, there is also a directed pairwise property and a directed local property, and the D separation is the directed local property, and they also turn out to be equivalent. Almost more or less. I think what Sullivan says is correct. But I know that for one of the steps also over in the directed case, you need the 5th axiom. And so it would be convenient to know that all probabilities are positive. Okay, now, so you can see that these characterizations would be useful for people who are using these things in practice, because as we were kind of discussing in the break, if you start completely afresh, not knowing anything, you will maybe start by collecting a lot of data, and then you'd like to figure out what the graph is. And so if we assume the positivity, so we don't have to work, if we sort of know that nothing is impossible, if we know that nothing is impossible, then all we have to do is look at the joint distribution of each pair of random variables, given all the others. Well, that's a complicated thing, but it's less than looking at all of these. We only have to look at a relatively small number of conditional distributions, unfortunately depending on many, many parameters, because all those conditional distributions depend on all the values of all the other variables. So there's an awful lot to be checked. But it's still less than checking all of this. And in the case if you would know in advance that all your random variables have got a joint multivariate normal distribution with a non-singular covariance matrix, then all you have to do is write down the covariance, is to estimate the covariance matrix of all your data, which people have been doing ever since there are computers, psychologists and biologists and so on have been hitting the button SPSS package and getting a huge matrix of all correlations, sample correlations, estimated from the data, and then you invert that matrix, and everywhere there is a 0, you leave out the edge. And the trouble is, when you invert that big matrix, actually you will have lots of zeros. Sorry, you will have lots of numbers which are small but not 0. Mm-hmm. And actually, if you have got more variables than cases, you won't be able to convert it in either. It'll be your sample covariance matrix will be singular, because the observations, even though they have like maybe they have dimension 10 or 100 or whatever. So maybe the observations now, you could think of them as 100-dimensional points, but you only have observed 20 people, so those 100-dimensional points are all going to lie on a 10-dimensional or 9-dimensional hyperplane or whatever. Anyway, but this is sort of the one of the doors into learning learning the model, so actually deciding the graph, or saying if the data confirms your previous ideas about the graph. So people from psychology or biology or genetics may have hypotheses about what graph structure should exist for these variables, and you can test them with data. But in particular by knowing things like this. Okay, so there is another one, there is such a similar list for these, but I won't reproduce them now, especially because I'm not quite sure if one of them is correct. But because I've seen another one which I do believe is correct, and it looks different. So I'm not sure if Solvent is entirely reliable there. Okay, now that's one sort of big thing about graphical models, is whether you can characterize them probabilistically in a more small way. Another thing is whether you can characterize them it's what are called factorization properties. If you suppose we assume there is a joint probability density of all the random variables. In particular, that's the case if they're all only take finite values, finitely many different values, then we just have a load of discrete probabilities. Can we, if we know this model is true, or if we know this model is true, can we say something nice about a joint probability mass function of all the random variables? And so on each side there's a theorem, and on this side it's almost trivial. Yeah. And so let me start on this side, and let me tell you. So I erase those moralized, those forced marriages, and shotgun weddings. So the shotgun weddings are gone now. Now, I said you can think of this in a causal way, and that's part of the idea that the scientists' knowledge of causality about the field we are talking about will enable them to already to be able to know some things about arrows and directions. Now, important property of DAG is that you can number the vertices, you can order the vertices in such a way that arrows only go forwards. And proof is by induction, I suppose, or something like you first of all pick an individual who has no parents. Well, first of all you have to show that there are individuals with no parents. There have to be, or there would be infinite.
It's finite and there are no cycles.
There is finite and there are no directed cycles. Yeah, so it's very elementary. And you can write the variables in a sequence. And arrows only go from left to right. And of course many arrows are missing, but there are some arrows only going in this direction. And this is in vertex 1, vertex 2, vertex 3, up to vertex n, say. So you can always arrange the vertices along the line in an ordering, in such a way the arrows only go forwards. And probabilistically what this model is saying is something very simple, namely how I would use my computer to simulate observations from this joint probability distribution. In other words, if I knew the joint probability distribution of everything, how could I generate 1,000 individuals who have the values of all their variables jointly distributed in that way. What I would do is, first of all, I would go to a root node, so a vertex with no parents, and it doesn't matter which one I take, but it's going to be number one, and I make with my computer a value of that random variable using the marginal distribution of that variable. So, for instance, this is whether the person is a male or female. I toss a coin to decide if they're male or female. Okay, that's probably going to have influence on other things. And then I'm going to look at the next one. Now, either there are arrows coming from the left to variable 2 or not. If there are no arrows coming from the left, I simply pick a value for this random variable independently of what I've done so far. So in such a situation, this one could also be the first, in fact. But I use the marginal distribution of variable 2 to make my computer give you a possible number, which, or whatever, or hair color, or whatever it is. And I go on. Now, occasionally I will come to a vertex which has got parents. And they must be to the left. And I simply, what I do is I make a value of variable 3 according to some rule or whatever. The probability distribution of 3 may depend on the values of the parent node. So better to take another one where there's not everything. Well, suppose this arrow was not there. So I first make variable 1, then I make variable 2, next I make variable 3, but I may need to know what the value of variable 2. And the probability distribution I will use for the third variable will depend on the second variable. And so I go to the end. So there's the joint probability distribution can be expressed in a sequence of conditional distributions of each variable, given only the parents, not everybody to the left, but given only the parents. Now, from what you guys now already know about conditional independence, this means that this variable, given its parents, right. If I only look at the variables from here to here, here's variable v, then this variable is independent of the others given the parents of this variable. So I could write that like this. So I've numbered them, and then I can talk about xn is independent of x, everybody up to the nth. So Sullivan would call that xn minus 1.
And n is a different one from the n?
Yeah, sorry, that is n is a different, it's a bit of k or something. N minus, now I need, no, I don't need any new notation, minus parents of k, given x parents of k. So we only look at the variables in the order in which we've taken them. And there are many possible orderings in general, but we have picked one. And then we can this is one of the deseparation properties. This set does deseparate these vertices from these vertices. So this is a conditional independence which we do know, we're entitled to use, and we can base them all together to give you the joint distribution of all the variables 1 up to n in the way I described. And to write it in a fancy way, so for instance, in the discrete case, this implies, let me write little p for x. This is, there should really be an index on the function to say which variables I'm talking about. But I'm being a lazy statistician and we often assume it's obvious from the context. So this is the joint mass function of all these random variables, evaluated in this particular list of values of all these variables. So this is just the probability capital P, x1 equals little x1, comma, capital X2 equals little x2, and so on up to the end. It factors, and moreover it factors in a recursive way. Products from 1 to n of v, products of k. Yeah, so v is now n. I've labeled variables in a convenient order, in an order respecting the order in the graph. The probability that the kth variable takes the particular value we have listed here, given the particular values which the parents of k have taken. So this should be true for all k. So the DAG, say discrete case, make things easy. Suppose all these sets are finite. Then we just need to talk about the joint probabilities and the conditional probabilities of any variable given others. Some of them may be not defined if there are things which have probability 0, but that doesn't matter because they will always get multiplied by 0, and so they won't cause any trouble. And okay, so here I've just redrawn the graph, right? Just redrawn the graph and renamed the vertices. And the graphical model holds in this context if and only if this for all k, and that holds if and only if this for xv in the product of the outcome species. So okay, so in this case there is a beautiful and useful and powerful and elementary, completely elementary, very, very trivial expression for the joint probabilities, and hence from these you could get all the other probabilities you want. And if you know that all these probability distributions here have nice algebraic properties, then you can say nice algebraic things about this one. So if you know these belong to exponential families and blah blah blah, then you take logs if you're allowed to and look at their sums, you'll get toric ideals and all kinds of wonderful things, which I apologize that we missed the 2 chapters where he actually shows how you can use some of that fancy stuff to say something about practical statistical tasks like estimation and testing. Those were chapters, I forget which, but we skipped them because I was greedy and I wanted to find out what he did with graphical models. So for that there is a recursive factorization of a very nice form, and really these models are rather elementary models because you can write everything very explicitly, and maybe later mention some more complicated graph theory. Okay, now I think I've got just enough time to do the corresponding factorization here, which is turns out to be very elementary. Actually, in the case of positive densities, and this is called, I think it's called something to do with Gibbs. This is where mathematical physics terminology comes up. So I'm assuming an undirected graphical model, a graphical model belonging to an undirected graph, and I suppose there exists a joint probability density. So that's certainly the case if in the discrete case, and it may or may not be the case for other things. I don't say anything about zeros yet. We say the model or the joint distribution is Gibbsian if there exists a whole heap of functions which will be called phi c, and they're non-negative functions, and they're sorry, I'll write them in a lazy way to indicate what they're supposed to be functions of. They're supposed to be functions of the values of the variables whose label or name is in set C, where C is a clique of the graph. Now there are two different notions of what a clique is, and for me it was always a maximal complete subgraph, and for other people it's often just a complete subgraph. I don't know how many of you do lots of things with graph theory all the time.
It's any, for me it's just any complete subgraph. And
Yes,
then
and
you
for
have-
Sullivan also.
Yeah, and then you have the maximum complete,
Yes.
which is the maximum complete subgraph.
Yes, so some people talk about completes and maximal complete, and other people talk about complete and of which some are called cliques. That was how I was educated. Sullivan talks about everything which is complete, he calls a clique. Well, it doesn't matter. Okay, so it actually doesn't matter here. It's not going to make a difference because otherwise we just change the functions. But if you prefer, so if you like, I could write is a complete subgraph, or I could write is a maximal complete subgraph, and it will still be true because it's just a question of redefining these functions which are very, very not uniquely defined. There are many, many ways to find such functions, such that Px is product, so that means of everything, right, capital V is a subscript, product of C, sorry, phi C of x, C. Full stop. So this, yeah. So you can, and these functions are called potentials. Sometimes they're logarithms, if they are positive, are called potentials. And this has a connection to mathematical physics, that's why they're called potentials.
Sorry, I was writing down something and now I don't understand anymore what you
Sorry.
wrote. No, it's my fault, sorry. But
No.
there is a phi c, or there is a c, and you take the product over all c?
Okay, sorry. If, so if there exist functions
Oh, for all.
phi c,
For every C. Yes.
for all C, a clique of G, and you can use whichever definition of clique you prefer here. Yeah, so if we would start with writing this expression where C goes through all the complete subgraphs. And every complete subgraph is a subset of a maximally complete subgraph. You assign the not maximal ones to a maximal one and multiply the functions, and then you get a similar expression with new functions, but the C only running over the maximally complete. And conversely, you just let all the other functions be 1, and then it's also the other way. So it doesn't matter, but it's often useful to think of the C here as being only the maximally complete, only looking at the maximally complete subgraphs. Okay, now, so now, first thing to say is these have to be non-negative functions. First thing is, I can tell you that if a joint density of this probability of these random variables has this shape, then the graphical model is true. In other words, it's not written anywhere anymore. XA is independent of XB given XS for any A, B, and S, such that S separates A from B. And the proof is very simple. First of all, it's sufficient to prove the result for A, B, and S, which together make up everything. Because if I know that it's true for A, B, and S, which together make up everything, then I can delete some of the variables from A, delete some of the variables from B, and it's still true. Conversely, if S separates a small set A from a small set B, then we can assign all the other variables to one side or the other, grow A and all grow B, or both, such that S still separates A from B, but and now we're talking about all the variables. And then we use axiom number whatever, one of the easy ones, but you can actually drop variables here. So now, please notice that if S separates A from B and together they make up everything, then no maximally complete set can intersect both A and B. It can intersect A and S possibly, and it can intersect B and possibly also S, but they can't intersect both because then A and B wouldn't be separated, because they would have a non-empty intersection inside the cube where everything is connected. So that means when I write down this expression here, we can put the C's all to one side or to the other side, and we can write the function we get as some function called f of the A variables and possibly also the S variables times another function of the B variables and possibly the S variables. So now I'm supposing that, I'm looking at everything now. I'm supposing S separates A from B, and I assign each phi C either to the left side or the right side. Now this is one, in the case of that you have a probability density, implies that XA is a variable, random variables of XA are independent of XB given XS. So we have shown that the Gibbsian representation puts us in there, ensures we are in the graphical, ensures the graphical model is true. Okay, now wouldn't it be wonderful if we could do the converse? And we can if the probabilities P, X, V are all positive. So So this is a hammer, different hammer, see? It's like so he mentions this theorem has a long history, which you can find some of it there, and indeed it started off being maybe conjectured for a while, and then proven by a whole lot of different people almost at the same time, all with very long and different proofs, and then finally someone came up with a very, very, very short proof. So which I will now, which he reproduces. And of course you all know, you all know Mobius inversion. So that's where it sort of turns around. It turns around Mobius inversion and such a characterization of conditional independence. If you can write a joint density like this, if there is a joint density and you can write it like this, then these variables are independent of these variables given these variables. So pivot handles. And Clifford is Clifford, who's known in statistics and worked in spatial statistics. And Hammersley is a very famous list, I suppose. But anyway, Clifford is not the Clifford from algebra. Okay, this, I forget when it is. So, okay, positive density and graphical model. Nice Gibbsian. So I have to show that I can write the probability density in this way. And so it's, when we look at this formula, we've got no idea what we should take for these functions, and there are many, many things we could take. And so it sort of hinges on having a brilliant guess for what the answer could be, and then showing that it works. So what we do is we define some functions as follows. So first of all, I pick a y in the product of the xv's. So that's, I pick a sort of reference outcome of all the variables. And then I define phi c of, so it's got the function of the values of the variables inside C, and here C is going to be anything, any subset, not just complete or cleats or whatever, but just anything. And then we'll show that the phi I've chosen is equal to 1 for all non-complete subsets C. And we do the following. We write down we take the product over all subsets, sorry, am I writing? Yeah, like this. Okay, so let me write S. All subsets of C, Y, define, I think there was something else I had to choose. Oh no, that's later. That's later. So the first thing is easy. P, X, X, S, Y, V minus S, to the power minus 1, to the power number of elements in C minus S. Yeah. That's very, very simple formula, but it's so I'm multiplying and dividing by a whole, each of these things I'm either multiplying by it or I'm dividing by it, so we want them all to be positive. And we need that P is positive everywhere because anything can turn up here, more or less anything. Not actually anything, but a lot of different possible arguments of the joint mass function of everything can turn up there. Okay, now I say Möbius inversion tells us that P of x everything is the product over all subsets of V, complete or not, of the phi c's of xc. Yeah, I just say Möbius inversion, but you can write down the 2 lines of algebra to prove it if you want to. Because it's essentially, you substitute this in here, and then you reverse the order of taking the product, and then you notice that everything cancels except the one you want. Okay, so we know that, so it remains to be proven that phi c is identically 1 if C is not complete. Phi C is equal to 1 if C not complete. Okay, so we pick a C which is not complete. So there exists an I and a J in C, and they're going to be different, such that I is not a neighbor of J. And then we write this product, we distinguish between whether S contains one or both of these two. And we get that phi C of xc is the product over S. This is now different S. S contained in C minus I and J, contained in C minus I and J. So I'm looking at this, the S's here which don't contain that variables I and J, but I'm going to consider both the case when you put I in and you put J in and you put both in. And the answer is that you get something complicated, V of x s. So first of all, when they're both in, you get xi and xj, and you get the rest, y v minus s. And you're also going to get, well, there's going to be a power here, and it's going to be the same power as before, minus 1 to the number of elements in C minus S, but the S is different. So here is the case, I've taken 2 elements out of S, so this has got the same sign as it did before. And here I've taken both out, xs, yi, yj, yv minus s together with I and j. Sorry, this is curved
We have just
brackets.
written yv minus s instead of yi and yj and y.
Sorry, where? Here?
We've written, instead of writing the 3 y's, couldn't we just write yv minus s once? Or maybe I don't understand the notation.
No, we could.
Okay,
Yeah.
it would be the same thing. Yep.
It's the same thing, according to this solving notation. According to this statistician's notation, it's exactly the same thing. But I want it like this because oh, sorry. Yeah, I should have done this here also. Yeah, so you turned up a mistake. So there's xs, and I add in I, and I add in j with x, and then I want the y for all the rest. Now this and this are the same. Okay, now downstairs I'm going to be lazy, I'm going to write the same thing, but with xi, yj, and xj, yi. So there are 4 p's here, and the xs is the same everywhere, and this is the same everywhere, y of v less s and less ij. No, and this says, this is equals 1 if, or I could say because that xi is independent of xj given everything else. And this is the expression for conditional independence, which Sullivan likes best, because it's a rational function, and in fact you can write it as this is equal to this. It's a binomial in the basic probabilities of interest. Okay, so I have to stop. So I will stop. Thank you. So what I didn't tell you was what this has anything to do with algebra. Geometry, and there are a couple of theorems at the end of the chapter which do make a link, but they're not very easy to decode if you haven't studied carefully the exponential families chapter. And we need more than just the basic thing which we learned in the exponential families, and the exponential families and the what was the other chapter? Fisher, the Fisher independence thing. Yeah, the Fisher test thing. We sort of didn't look at the examples of the Fisher